Welcome to the class on artificial neural networks. This video discusses a gradient descent method, which is an alternative to the perceptron algorithm for simple perceptrons. So far, we had worked with a threshold unit, a sharp threshold at the output, and now we assume that the output unit has a smooth activation function. So we work as before in n+1 dimensions, which means the threshold is not explicit. The threshold is implicit and implemented as one extra input unit to my output neuron. And we can choose different forms of this nonlinear function, but a standard form is this one. I write it in two different forms. It's sometimes called the sigmoidal output unit. It goes from 0 and saturates at 1, so it has all positive values. And since we work in n+1 dimensions, the threshold is implicitly here at 0. Now note that this sum over all inputs in n+1 dimensions still amounts to a hyperplane that runs through the origin in n+1 dimensions. That's the geometric picture I had shown earlier. And now the question is, how can we learn the weights in such a network? And the idea is that of supervised learning. We have a classifier. In our case, the classifier is this simple perceptron with a sigmoidal output unit. And here in this specific example, the output is 0.2, but the output should be 1. So I have this mismatch, I have this error. And now I use this information on the error to optimize the weights that connect the inputs to the output unit. So these weights here, the weight vector in n+1 dimensions, this is really the set of parameters we are going to tune, and we use this mismatch, we use this error. I said that the error is usually measured by a loss function. Here we use, for the sake of simplicity, the quadratic error. It's important that it's not just the difference. The difference itself could be positive or negative. However, an error should always be positive or 0. It shouldn't be negative. And so one way of doing this is to use the square here. You could also use the fourth power, or you could use absolute values and just the first power. There are different possibilities. The quadratic error is one of the standard choices. So what we compare here is the target output with the actual output of my network. For example, for one pattern mu, pattern number 7, the target output could be 1, and the actual output is 0.0. I have a difference of 0.8, and I square this difference. The factor of 1/2 in front has no deep meaning. And this was the difference, or the error, the quadratic error for one pattern, but in fact, we have to consider all the p patterns of my database, and therefore we sum over all these p patterns. And now the idea is that we change the weights such that the error gets smaller. Now we have many weights. I pick one weight k equals 3, for example, and as a function of this weight, we see that the error takes different values. And now the idea is to change the weight such that I have a change of this weight k, so I have delta wk, and the weight is such that the error goes down. So after the update, the error is smaller than it was before. And now you see that here I have a red function. This is my error function as a function of the weight, which has a negative slope. Now but in order to go down, I have to increase my weight, wk, and therefore the weight change should be proportional to minus in direction of the gradient. And the factor gamma here is the learning rate. So gradient descent does not guarantee that I find the global minimum, which would be here. Gradient descent moves down and eventually it will get stuck in a local minimum. Nevertheless, often, in particular in big neural networks, deep neural networks with many neurons, then the local minima could be already quite a good minimum. So now we need to calculate this gradient. So here's the gradient summed over all p patterns. And that's the first thing we should calculate. We calculate the gradient. And then we say, in a second step, well, actually, in the perceptron algorithm, we used one pattern at a time. So let's try to do this. Limit to one pattern at a time and cycle through the patterns. And then the other question is, well, for the perceptron algorithm, we had this nice geometric interpretation. Can we get a similar geometric interpretation for the case here, for the gradient descent algorithm? And before doing this calculation, I want you to actually start this calculation. So please pause the video now for as long as you want, might be 5 minutes or 10 minutes, and try to get through the calculation as far as you can, and only then rerun the video again. And so here we are now for the calculation. I hope that you have tried before, and now let's do it together. So my error function is the factor of 1/2, and I add another factor 1 over p. That's also a factor that's not important. Both factors are just for reasons of mathematical beauty, and you will see where the beauty comes from in a minute. And then I have my target value, t mu, and I compare with my actual output, y hat for pattern mu, and it's the squared error. Now, let me plug in the fact that we have a nonlinear transform, some sigmoidal, and we run from k equal 1 to n+1, I mean n+1 dimensions, wk xk mu, because here it's pattern mu. So t mu minus this squared sum over mu 1/2 1 over p. And now let's walk down and take one specific weight. I find it personally instructive to work with one specific weight and do the gradient sort of per component and not immediately in a vector notation, because it's easier to see where the different terms come from. So now, how would we do this? So I take the gradient, dE dw3, and then I need to copy. I have 1/2 1 over p, and then I have sum over mu. So far, everything is a copy. And now I have to use the chain rule. So I have here the outer brackets with a square of 2. So taking the chain rule means this exponent of 2 comes down. So I have 2 times. And then I just copy whatever is inside these squared brackets. So this is t mu minus g of sum over k wk xk mu. And now I have to take the derivative of what's inside the red brackets, so what's inside here, with respect to w3. I'm interested in w3. So where does W3 appear? Well, it would appear here. But that's inside this function g. So I have a g prime evaluated at this location. And then I have a minus sign, which I put down here. So this is the minus sign. And then I have to take the derivative of what's inside this g function with respect to W3. And now you see that this sum runs from k equal 1, okay, but the term k equal 1 does not depend on W3. Then it goes to k equal 2, then it goes to W3. Okay, but if we are at W3, then we take the derivative. What remains is the term x3, the third component, x3 mu. And this is the algorithm. So we can now cut out the 1 over 2 and say this is the gradient descent calculation. Now, I said here in the title, we distinguish between batch and online. This is called batch. Batch means that I use all p patterns. In my error function, I have a sum over all p patterns, which remains here and which also shows up here. But then we saw in the personal algorithm that it actually might be nice to do something online, take one pattern at a time. So what you do for an online algorithm is quite simple. You cut out the sum over the patterns, and then this gives an online algorithm which looks like this. Let me write it like this. Delta W3 is minus gamma, and then I have dE dW3, but I use the online version where I have cut out this term. So now the 1 over p is gone. So I have a plus gamma because of the minus sign cancels with this minus sign. And then I have T mu minus G of W k xk mu. And then I have my G prime. And then I have my x3 mu. So this is now the online algorithm. Now what is G of WKXK? Well, we used it up here. That is just y hat mu. So I can also write it as T mu minus y hat mu. And then I have another factor G prime. Let's write this as just some scalar. So G prime is just a number, it's a scalar. T is the output value, it's a scalar. Y hat mu is the output of the actual neuron, is a scalar. So this gives delta mu. And then I have an update. Delta W3 equals gamma delta mu times x3 mu. And now we make another observation. Here's the index 3, here's the index 3. So I can renote this in vector notation and say delta W is gamma times delta mu, that was the scalar, and this turns now into the vector x mu. And so this is now my online algorithm in vector notation. I said at the beginning that I pick out W3, but this was just one choice. This is true for any component. I can collect the components back into a vector, and this is now my update rule. What is this delta mu? The delta mu was defined here. So the delta mu is T mu minus y hat mu times G prime. So now I have an update rule, which I will write down again. After the presentation of my pattern mu, I update the weight vector by delta W, which is proportional to x mu. And then I have a factor, and the factor delta mu is proportional to the signed output mismatch. And that's what we just saw. Delta mu is T mu minus y hat mu times G prime. But I'm interested in this vector interpretation. So the change of the weight vector is proportional to the data point that's applied. And this change is always implemented whenever I have a non-zero value of delta of mu. So a point here that lies on the positive side of the hyperplane might still call a tiny change in the weight vector in this direction. A point here might cause a tiny change in this direction, and so forth. So it's not, so points that are correctly classified in the sense that they are already lying on the correct side of the hyperplane may still lead to a small change of the weight vector. And now if you look at this formula for the update, well, this is in fact absolutely similar to the perceptron algorithm. The only thing that has changed is the definition of this delta. For the perceptron algorithm, it didn't have the term G prime, and the output for the perceptron algorithm was always a binary output, 0 and 1, whereas here it's this smooth output. But the geometric interpretation is exactly the same. So here's the algorithm written now down as stochastic gradient descent for the simple perceptron. And I remind you that we are working always in n+1 dimensions, so the threshold is integrated as an extra input. You can start with a relatively small learning rate. You have p patterns in total. Then you fix a number of epochs. There's, in contrast to the perceptron algorithm, there's no guarantee that it stops after a finite time, even for linearly separable problems. And so you have a counter p times m. You choose a pattern mu, a randomly chosen pattern. You calculate the output. Then you update with this formula that we just derived. Then you increase your counter, and you stop if the changes during the last p patterns, you did p times m iterations during the last p patterns, was acceptably small. Otherwise, you run another loop over p times m. And you may want to decrease gamma towards the end of learning. So, what have we seen in this series of videos today? I put emphasis on the notion of learning and classification as a geometric problem. And the geometric problem can be illustrated by this discriminant function of classification, which is some surface in this high-dimensional space, and it can come either as a linear surface, which means a hyperplane, or some nonlinear discriminant function. Now, a linear discriminant function can only give zero error if we work with linearly separable problems. So it's important to distinguish this conceptually. Linearly separable is a statement about the problem. It's a statement about the database versus the question whether discriminant function is linear or nonlinear is a statement about the model, the type of neural network that you actually use, that you implement. Then we saw this perceptron algorithm. We also saw stochastic gradient descent for simple perceptron. And interestingly, both give the same geometric picture. Learning amounts to a rotation of the separating hyperplane in n+1 dimensions. And there is reading for this week. I like the book of Bishop, and in particular for this kind of approach. And at the beginning of this lecture series, I gave a couple of motivational examples, and you find good reading in these two in these two references. And that's the end for this week.